this lecture, we will continue our discussions on wave particle duality and will give a very heuristic derivation of the Schrodinger equation. And then we will discuss the Dirac delta function and Fourier transform. That will be a bit of mathematics, but that is necessary to understand the solutions of the Schrodinger equation. So, this is the second talk on quantum mechanics, and as I mentioned in my previous talk, de Broglie wrote that I was convinced that the wave particle duality discovered by Einstein in his theory of light quanta was absolutely general and extended to all of the physical world. And it seemed certain to me that therefore the propagation of a wave is associated with the motion of a particle of any sort, photon, electron, proton or any other. Now actually after de Broglie wrote this, the experiments, the diffraction pattern by electrons were observed much later. So that is why de Broglie's contribution is considered to be outstanding. He predicted the wave nature of electrons. He said that it could not just be for photons, it would be for electrons and protons and neutrons or whatever you can think, or alpha particles or anything that you can think of. And it was only later he made this prediction around 1923 or 22, and the experiments were carried out only in 1926 or 27 I think, the famous diffraction experiments of electron. So, the wave particle duality led to the development of quantum mechanics in 1926. It led to the famous Schrodinger equation, and the Schrodinger equation is given by IH cross delta psi by delta t is equal to H psi. So, let me tell you right in the beginning, if you ask me the question that what is an electron, what is a proton, is it a particle or a wave? Some people would answer that it is both. That answer is not quite correct. The correct answer is that it is neither. So, the electron or the proton is neither a wave nor a particle. It is described by a wave function psi, which is a solution of this equation. In 1926 itself, Max Born formulated the new standard interpretation of the probability density function for psi star psi, for which he was awarded the 1954 Nobel Prize in Physics. So, mod psi square d tau represents the probability of finding the particle in the volume element d tau. And since the particle has to be found out somewhere, so the total integral, the total probability must be equal to 1. This condition is known as the normalization condition. Anyway, we will discuss that, but first I would like to give you a heuristic derivation of the Schrodinger equation. Now, let me take a plane wave. A plane wave is described by a wave function psi, a one-dimensional plane wave. So, you have a into e to the power of I kx minus omega t. So, this is a plane wave propagating in the plus x direction. Now, in this equation, I somehow inject the wave particle duality. So, as was put forward by de Broglie, that the momentum of a particle is related to the wavelength by h by lambda. This equation is known as the de Broglie relation. So, I divide and multiply by 2 pi. So, h by 2 pi into 2 pi by lambda. This quantity is defined as h cross. So, this is h cross k, where h cross is defined to be equal to the Planck's constant divided by 2 pi. And it has a value about 1.1, something like that, into 10 to the power of minus 34 joules second, something like that. Then in this equation, we write the Einstein's equation, which is h E is equal to h nu. Once again I divide and multiply by 2 pi. So, this is h by 2 pi into 2 pi nu. So, this is h cross and this is omega. So, this is h cross omega. So, I get k is equal to p by h cross and omega is equal to E by h cross. And I substitute this in this expression. So, therefore, I rewrite a one dimensional wave psi x t is equal to A into e to the power of I k x. K will be p by h cross. So, I by h cross p x minus omega t, sorry, minus E t. Let me do this again. We had just now said that psi of x t, the one dimensional plane wave, is equal to A e to the power of I k x minus omega t. So, then we showed that k is equal to p by h cross and omega is equal to E by h cross. So, I substitute this here and I get A e to the power of I by h cross p x minus E t. Then I differentiate, partially differentiate with respect to x and multiply by minus I h cross. So, minus I h cross delta psi by delta x, this is equal to minus I h cross, and if I differentiate this with respect to x, I will get I p by h cross. So, multiplied by I p by h cross times the whole thing. So, therefore, this is psi. So, h cross cancel out, I times I is minus 1. So, minus minus is plus 1. So, this is p psi. In fact, this relation suggests a momentum operator for p, because p is associated, therefore, p operating on psi is the same as p is associated with minus I h cross delta by delta x. This is not rigorous, but we will write this down there and we will discuss more little later. I differentiate this again. So, I get minus I h cross times minus I h cross, that is whole square, again differentiate. So, delta 2 psi by delta x square. So, I multiplied by minus I h cross, and if I differentiate this, then again I will get minus I h cross into I p by h cross, and therefore, a little algebra will show that this becomes p square psi. So, this suggests that p square is equivalent to the operator minus h cross square delta 2 by delta x square. So, this quantity minus minus is plus, I square is minus 1. So, I get minus h cross square, and I divide by, say, the mass of the particle. Say mass of the particle is m, let us suppose, minus h cross square by 2m delta 2 psi by delta x square is equal to p square by 2m into psi. Now, let me write down the wave function once again. So, I have psi of x t x comma t is equal to e to the power of I by h cross p x minus e t. Now, I partially differentiate with respect to time, and I write I h cross delta psi by delta t, and I obtain I h cross comes from here, and then if I differentiate with respect to time, then I will get minus I e by h cross and the whole thing again. So, this will be times psi, psi as a function of x comma t. So, I times I is minus 1, minus 1 into minus is plus, h cross cancels out. So, you get E psi. Just now I had derived another equation which is minus h cross square by 2m delta 2 psi by delta x square is equal to p square by 2m psi. Now, for a free particle, the total energy is the kinetic energy classically. So, you have E is equal to p square by 2m. So, this side is equal to this side. So, this must be equal to this. So, I h cross delta psi by delta t is equal to minus h cross square by 2m delta 2 psi by delta x square. This is known as the one dimensional Schrodinger equation for a free particle. Now, the derivation that I have given is far from rigorous, but once I have derived this equation, I will study its solution. So, let me do one more thing, that I had derived two equations. First, I derived I h cross delta psi by delta t is equal to E psi. I had derived this. Then earlier I had derived minus h cross square by 2m delta 2 psi by delta x square is equal to p square by 2m into psi. Now, let us suppose the particle is in a potential field. So you have the total energy is the kinetic energy plus the potential energy. So I write this equation, V psi is equal to V psi. V is the potential energy. So E is equal to P square by 2m plus V. So this must be equal to this plus this. So this is the rigorously correct Schrodinger equation, one dimensional Schrodinger equation for a particle in a potential field described by V of x, delta 2 psi by delta x square plus the potential is so much and psi of x. So this is the Schrodinger equation for a for a particle in a potential field. When this is 0, when it is a free particle, then this is 0, then you have only these two terms for the Schrodinger equation. So let me go back to my slides and let me give you, I will repeat the heuristic derivation of the Schrodinger equation. So I write a plane wave propagating in the plus x direction as a into e to the power of I k x minus omega t. Now P is equal to, this is the de Broglie relation, h by lambda. So I multiply by 2 pi and divide by 2 pi. So this quantity is h cross and this quantity is the wave vector k. So this is h cross is known as the Planck's constant, and E is equal to h nu. I divide and multiply by 2 pi and I get h cross omega. So this is the known as the Einstein's equation. So I substitute P and E in this equation, that is for k you will write P by h cross, for omega I will write E by h cross. So I get this. I differentiate with respect, partially with respect to x, multiply by minus I h cross, and I will get minus I h cross times I by h cross P. So that will become just P times psi. So P can be associated with the operator minus I h cross. P psi is equal to minus I h cross delta psi by delta x. I differentiate it again. Here I am sorry, I have written the mass as mu minus h cross square by 2 mu delta 2 psi by delta x square, and I p square, when if I differentiate this twice, so I will get I by h cross whole square p square. So h cross square will cancel out, p square psi, which is the kinetic energy, times psi. P square by 2 mu is the kinetic energy. And if I differentiate with respect to time, you will get E psi. So for a free particle, E is equal to P square by 2 mu. So this quantity should be equal to this quantity. So for a free particle, E is equal to P square by 2 mu. So I get the one dimensional Schrodinger equation for a free particle. For a particle in a potential field V of x, E is equal to P square by 2 mu plus V of x. So E psi is equal to P square by 2 mu plus V of x, and then you get this. So this is rigorously correct one dimensional time dependent Schrodinger equation for a particle in a potential field V of x. So one writes this quantity is the operator, this is P square by 2 mu. So this is the operator corresponding to the total energy. So that is known as the Hamiltonian. Richard Feynman As you all know, he is one of the outstanding physicists of the 20th century. He writes, where did we get that equation from? And he says, nowhere. It is not possible to derive it from anything you know. It came out of the mind of Schrodinger. So, I have given a very heuristic derivation which lacks rigor. Somehow, I have been able to reach the Schrodinger equation. And then I will try to get results by solving the Schrodinger equation. This equation was first obtained by Erwin Schrodinger in 1926, and I will obtain the solutions, and then we will find that this compares very well with experimental data. So, that is the success of quantum mechanics. That is the success of the Schrodinger equation, for which Schrodinger got the Nobel Prize, I think in 1933. So, we have obtained the Schrodinger equation. Now, we will use the Schrodinger equation to study its solution. However, we will digress here for a moment, and we will do a little bit of mathematics. And in this mathematics, we will try to define what is a Dirac delta function, and we will also discuss what we mean by the Fourier transform of a function. Even before that, let me mention that this integral e to the power of minus x square dx, let me evaluate this integral. So, from minus infinity to plus infinity. This integral, let us suppose I write as I. So, you will have I square will be this times this. So, again the same integral, since it is a definite integral, I will write this as e to the power of minus y square dy. So, this is over the entire xy plane. So, this will be minus infinity to plus infinity e to the power of minus x square plus y square dx dy over the entire xy plane from minus infinity to plus infinity. This integral is very easy to obtain. So, you will have, you define the polar coordinates, rho is equal to x cos theta and I'm sorry, x is equal to rho cos theta and y is equal to rho sin theta. So, you have here this as the x and y coordinates and these are the polar coordinates. So, this is rho. So, this angle is theta. So, this is rho cos theta is x and rho sin theta is y. The area element in this plane, as you all know, will be d rho times rho d theta, and x square plus y square is equal to rho square cos square theta plus rho square sin square theta, that is just rho square. So, I will have rho is of course positive. So, the theta integral is from 0 to 2 pi and the rho integral is from 0 to infinity e to the power of minus rho square rho d rho. This integral is trivial, this is 2 pi and this is half into e to the power of minus rho square with a minus sign with the limits 0 to infinity. At infinity this is 0, at 0 it is half. So, this comes out to be pi. So, I obtain the result that I is equal to, this is a very important integral which I would like all of you to remember, and we will use this very often. E to the power of minus x square dx is equal to under root of pi. I square was pi, so I is under root of pi. Using this, we can now evaluate this integral. So, let us suppose I have this integral e to the power of minus alpha x square plus beta x dx. So, this is from minus infinity to plus infinity. What you do is, as most of you may be already be aware of, you form a whole square of it. So, you get minus infinity to plus infinity e to the power of minus alpha, and then you get x square minus beta by alpha into x, and then if you want to make a whole square, you have to add and subtract beta by 2 alpha whole square. So, beta square by 4 alpha square, and then minus beta square by 4 alpha square multiplied by dx. So, this I can take outside. Please see, beta square by 4 alpha square minus sign into alpha, that is beta square by 4 alpha. So, this becomes e to the power of beta square by 4 alpha, and this becomes e to the power of minus alpha x minus beta by 2 alpha whole square into dx. So, from minus infinity to plus infinity, I define this as a z variable. So, I find that this integral becomes e to the power of beta square by 4 alpha and e to the power of minus infinity to plus infinity e to the power of alpha, say z square into dz, where z is defined to be equal to x minus beta by 2 alpha. So, that dx is equal to dz, and in order to evaluate that, you write down alpha under root of alpha times z is equal to y. So, you get dz is equal to dy by under root of alpha. So, you get e to the power of beta square by 4 alpha. So, 1 over root alpha and minus infinity to plus infinity e to the power of minus y square dy. Now, this we have just now evaluated. So, this is square root of pi. So, this quantity becomes equal to square root of pi by alpha e to the power of beta square by 4 alpha. This is a very important integral. I would request all of you to remember this. So, let me write this down once again, that the integral I is defined as integral from minus infinity to plus infinity e to the power of minus alpha x square plus beta x dx is equal to under root of pi by alpha into exponential of beta square by 4 alpha. This I would request all of you to remember this. Now, having done this, let me now go to the definition of the Dirac delta function. So, we will now discuss the Dirac delta function. And the simplest representation of this Dirac delta function is like this. Let me consider a point A on the x axis, this is the x axis, and I consider a rectangle, I consider a function, please see this, that which is 0 for like this, and then it becomes a rectangle function 2, 3. So, this is the point A, this is the point A minus sigma, and this is the point A plus sigma. So, that this line is 2 sigma, and I assume that the height of this function is 1 over 2 sigma. So, that the area under this rectangle is 1 over 2 sigma multiplied by 2 sigma. So, the area is 1 independent of sigma. So, I define a function r sigma of x which is equal to 1 over 2 sigma for x lying between a plus sigma and a minus sigma and 0 everywhere else. So, that the integral from minus infinity to plus infinity r sigma of x is equal to 1 over 2 sigma only from this limit. So, this is a minus sigma to a plus sigma dx. So, this is equal to 2 sigma. So, this is 1. So, let us reduce the value of sigma. So, let me reduce this, but if I reduce the value of sigma, the height becomes larger, and in the limit of sigma tending to 0, this becomes very sharp and very tall. So, in the limit of sigma tending to 0, this is one of the representations of the Dirac delta function. So, let me show you. I consider a rectangle function which is 1 over 2 sigma for x lying between a minus sigma and a plus sigma and 0 everywhere else. So, that the integral of this function from minus infinity to plus infinity. So, let us suppose it is 0 everywhere and then it is so much and 0 everywhere else. So, it goes from, I have taken a here to be equal to 2. So, it is a minus sigma to a plus sigma. So, the integral is 1. So, now I reduce the value of sigma. So, here sigma is equal to 0.4. So, 1 over 2 sigma is 1 over 0.8, which is slightly less than 1, and when you make it 0.1, so this becomes larger. When you become sigma even smaller, then the width becomes smaller, the height becomes larger, but in each of the 3 cases, the area under the curve is unity. In the limit of sigma tending to 0, we have a very narrow function and very tall function. The area under the curve is 1, that is one representation of the Dirac delta function, one of the many representations of the Dirac delta function. So, let me consider r sigma of x when sigma is small, so that it is very tall and this width is very small. I multiply this function by an arbitrary function of x. Now, the product of this function and the rectangle function in this region is 0. Product of 2 numbers is 0 if one of the numbers is 0. So, the product of f of x r sigma x is 0 excepting in the domain a minus sigma to a plus sigma. Why? Because r sigma of x is 0 here. So, therefore, f of x delta of x of minus a dx is equal to limit as sigma tends to 0 f of x r sigma of x. In this tiny interval, f of x can be assumed to be constant, because this interval can be made as small as you like, and in this interval r sigma is a value of 1 over 2 sigma, and when I integrate this it becomes 2 sigma. So, this becomes f of a. So, this is the property for any well behaved function f of x. If I multiply by delta of x minus a and carry out the integration, I will get f of a. So, this is the definition of the Dirac delta function. It is shown as a spike, an arrow of unit height at x is equal to a. But the area under the curve is 1. Actually, it is infinitely thin and infinitely tall, so that the area under the curve is 1. But it is shown by an arrow, usually shown by an arrow. It is like an impulse and has the property that any function, any arbitrary function multiplied by delta of x minus a dx is equal to f of a. Let me do this once again. That you see, what I have tried to tell you is that I have a very tall function, and this is 0 here, this is 0 here. Now, I consider another function. This is the rectangle function. I have another function like this. This is f of x, which is smoothly varying. Now, the product of this function and this function in this region is 0, because this is 0. The product of f of x and this function is also 0. So, the integral f of x r sigma of x dx from minus infinity to plus infinity is really between this limit and this limit, because the product is 0 everywhere else. So, this is actually from a minus sigma to a plus sigma f of x r sigma of x is 1 over 2 sigma dx. But if this interval is very small, then f of x does not vary too much in that variable. So, I can take it out of the integral and I write this is no more approximate. If sigma is very small, I can choose as small as I like. So, this becomes f of a into 2 sigma 1 over 2 sigma dx integral. So, this is equal to a minus sigma to a plus sigma. So, this is 2 sigma. So, 2 sigma cancel out and you get f of a. So, this in the limit of sigma tending to 0. So, I get the very important result that delta of x minus a is 0 everywhere else excepting at x is equal to a, where it has an infinite value such that minus infinity to plus infinity delta of x minus a dx is equal to 1. And then I have that minus infinity to plus infinity of a well defined function, well behaved function f of x into delta of x minus a, because the product is 0 everywhere excepting at x equal to a dx, this is equal to f of a. These three equations define the Dirac delta function. But what I have given you is just one of the representations of the Dirac delta function. Let me give you one more definition. I have here, let us suppose, a ramp function. Ramp function I take say like this. It has a value 1 here and 0 here. So, let me write this down with the blue color. So, a ramp function is 0 here, then it increases linearly and then it becomes 1 here. So, this is at x is equal to a, it has a value half. So, if the ramp function is defined as T sigma of x, then I write that this is equal to 1 over 2 sigma x minus a minus sigma. So, at x is equal to a minus sigma, this is 0. So, this is a minus sigma. At x is equal to a plus sigma, so this becomes a plus sigma minus a plus sigma, 2 sigma cancels out. So, that is 1. And at x is equal to a, this is 0. So, sigma by 2 sigma. So, at x is equal to a, it has the value equal to half. So, in this region from between a minus sigma and a plus sigma, T sigma of x has this value. Now, I take the derivative of this function. So, I have this ramp function which is 0 here, it increases linearly here and it becomes 1 here. If I take the derivative of this function, so dt sigma by dx, if you see this, if you just differentiate this, this is equal to 1 over 2 sigma. So, this is my r sigma of x, this is the rectangle function. So, the derivative of this function is, if you see carefully, that in this here it is 0, here it is something like this, and here beyond this it is 0. So, as I make sigma smaller, it becomes sharper and sharper. So, therefore, if I have a ramp function like this, if I have a ramp function like this, which goes like this and then it goes like this and then it has a 1 value, then the derivative of this function, because derivative is 0 here, derivative is 0 here, derivative of here is unity, then this is the rectangle function, and as I make sigma smaller and smaller, this becomes sharper and sharper. In the limit of sigma tending to 0, you will have the Heaviside unit step function like this. The derivative of this function, this is known as the Heaviside unit step function, and it is known as, it is described by as h of x minus a. The derivative of the unit step function is a Dirac delta function. So, h prime of x minus a is equal to delta of x minus a. So, let me show you in the slides that this is the ramp function. So, it is 0 here and then it becomes, when sigma is large, as you make sigma smaller and smaller, the slope of this function becomes larger and larger. In the limit of sigma tending to 0, this becomes a unit step function. I am sorry, here I have written as f sigma of x. So, this is the derivative of the ramp function, and in the limit of sigma tending to 0, it will become a delta function. So, this is the unit step function, this is known as the Heaviside unit step function, and its derivative is the Dirac delta function. So, whenever you have a discontinuity in a function, then its derivative is a Dirac delta function. Now, I will show you by a simple example, and you should be very careful in calculating the derivative. So, let us consider a function like e to the power of minus mod x. Now, e to the power of minus mod x, this means that this is equal to e to the power of plus x for x less than 0 and e to the power of minus x. So, psi is equal to e to the power of minus mod x, minus x for x greater than 0. If you take the derivative psi prime, this is e to the power of x for x less than 0 and minus e to the power of minus x, x greater than 0. And if you keep on naively differentiating this, it will become e to the power of x and e to the power of minus minus plus e to the power of minus x for x greater than 0. So, you will find that this is e to the power of minus mod x. So, psi double prime is equal to psi. Now, this is incorrect, because this function looks like this. So, its derivative has a discontinuity. The derivative has a discontinuity of minus 2 units. So, the derivative, if you approach from the left hand side, this is psi prime, has a value plus 1 and has a value minus 1 if you approach from the right hand side. So, at this point, at x is equal to 0, if you plot this, it will be something like this, but there is a Dirac delta function at the origin. So, let me illustrate this. So, you have here e to the power of minus mod x, a plot of the symmetric function. Now, its derivative has a discontinuity of minus 2 units. If the derivative has a discontinuity of plus 1 unit, then the derivative is if the function has a discontinuity of 1 unit plus, then its derivative is a delta function. But if it is minus 2 units, so psi double prime of x at x is equal to 0 is equal to minus 2 times delta x. So, you must remember that whenever a function has a discontinuity at a particular place, then its derivative is always a Dirac delta function. Dirac delta function multiplied by the amount of discontinuity. If the amount of discontinuity is minus 5, then the derivative will be minus 5 times delta x. So, in this particular case, the derivative was minus 2 units. So, the derivative at the origin is minus 2 delta x. In the unit step function, the derivative was plus 1. As I increase x, the discontinuity is plus 1. So, the derivative here is just delta of x. If a function behaves like this, that you have a function, it goes like this and then it makes a jump of say 5 units. So, at that point, the derivative will be 5 times delta x. So, this is here I have derived the same equation that which I derived some time back, that the integral I convert it into polar coordinates and I obtain that I square is pi. So, I will be equal to under root of pi. So, let me consider the Gaussian function. The Gaussian function, I write it as 1 over sigma under root 2 pi e to the power of minus x square by 2 sigma. So, let me write a Gaussian function like this, g sigma of x is equal to 1 over sigma under root of 2 pi e to the power of minus x square by 2 sigma square. Sorry, there is no integral sign here. So, it's a dumbbell function like this, it's a Gaussian function peaked at x is equal to 0. The integral of this function minus infinity to plus infinity, I can take sigma under root of 2 pi outside. So, the integral of this function is e to the power of minus x square by 2 sigma square dx. So, if you use the formula, so this will be 1 over sigma under root of 2 pi multiplied by pi by alpha. So, under root of pi, alpha is equal to 1 over 2 sigma square. So, this is 2 sigma square. So, this cancels out. So, this will be 1. So, the area under the curve is always 1 irrespective of the value of sigma. So, let me plot this. At x is equal to a, the width of the function at x is equal to say 0, the value is 1 over sigma. So, the value of the Gaussian function at x is equal to 0 is about 1 over sigma, or actually 1 over sigma under root of 2 pi, and the width of the function is about sigma. So, as I make sigma smaller, the width becomes smaller, the peak becomes sharper, but the area under the curve remains the same. So, therefore, this is yet another representation of the Dirac delta function, that delta of x is equal to limit of sigma tending to 0, 1 over sigma under root of 2 pi e to the power of minus x square by 2 sigma square. This is known as the Gaussian representation of the Dirac delta function. So, I come back to my slide and I have here g sigma of x I define as, when I have 3 equal to signs, that means 1 over, this is defined to be equal to that, and this factor is such that the integral under the curve is 1. So, this is obvious. So, this is I take the integral under the curve. So, I put y is equal to x by sigma under root of 2. So, this becomes very simple integration with the formula that I had given you earlier, and this integral is 1 irrespective of the value of sigma. So, I plot this. So, as the value of sigma becomes smaller and smaller, it becomes sharper and sharper, the width becomes smaller, but the value at x is equal to 2, or if I have a displaced Gaussian, here I have taken a is equal to 2. This corresponds to sigma is equal to 0.04, 0.4, this corresponds to 0.2, 0.1. If you make even smaller, 0.01, it will become taller and sharper. So, for sigma tending to 0, the function g sigma of x has all the properties of the Dirac delta function. So, this equation at the top is known as the Gaussian representation of the Dirac delta function. Now, in a room like this, let us suppose the distribution of energy of the molecules is given by the Maxwellian distribution. So, n of E dE represents the number of molecules whose energy lying between E and E plus dE. If I ask you the question, how many molecules have exactly the energy E is equal to kT? The answer is 0, because dE is 0. I want the number of molecules whose energy lies between kT and kT. So, dE is 0. So, in this distribution, the total number of molecules which have exactly the energy equal to kT is 0. But if we do have a number of molecules, let us suppose n1 number of molecules, which has exactly the energy E1, then to this I must add this Dirac delta function. So, delta function is a distribution, and so therefore, n of E dE represents the number of molecules n of E. So, let me summarize this by saying that if I have delta of x and x is in meters, then the dimension of delta of x will be meter inverse. If delta of E minus E1, if this is E is measured in joules, then this times dE will give the number of molecules. So, therefore, the dimensions of delta of E minus E1 is joules inverse. Here delta of x dx is equal to 1. So, therefore, if x is in meters, so dx has the dimension of meters, delta x will have a dimension of meter inverse. So, it is not just an ordinary function, it is a distribution. So, if you have let us suppose age distribution function of students in an university, if it is given by this n of A versus A. Therefore, n of A dA represents the number of students whose age lies between A and A plus dA. So, if I want to ask that what is the number of boys who have exactly the age 22 years, the answer is 0. But if we do have exactly 20 students who have the exact energy of 20 years. So, let us suppose there are 25 students who have the energy, who have the age exactly 20 years. So, then that is represented by this, and that will be represented by a Dirac delta function, and this dimensions of this will be age inverse. So, delta of x, if x is measured in meters, then it is delta of x is in meter inverse. If x is energy, then it is energy inverse. If it is time, then it is time inverse. So, we will continue next time on the other representations of the Dirac delta function and the Fourier transform theory. Thank you.